So far we have discussed the definition of continuity over the interval at the point and also for an arbitrary sets. We can extend that definition, we can define the continuity of function in an arbitrary metric space in a similar way, which we have defined in case of a point on the real line by choosing the in terms of the neighborhoods. So, we here just for the sake we define the continuity of the function in a arbitrary metric space at some point in the arbitrary metric space. So, suppose x d and y d are two metric spaces or metric spaces, okay, and E is a non-empty subset of X. P is a point belonging to E, P is a point belonging to E, and F is a mapping from E to E into Y, Okay. Then we say F is continuous at a point P belongs to E if for a given epsilon r greater than 0 there exists a delta which depends on epsilon r as well as the point say P, such that d of f x comma f p in the metric of y is less than epsilon r for all points x belongs to E, for which the distance from P in a metric x is less than delta. So, and if f is continuous, at every point of E, then we say f is continuous on E. Okay. So, the meaning is like this. Suppose this is our set a metric space x d and here is say metric space y d. E be a non-empty subsets of x and P is any arbitrary point in P is a point in E. F is a mapping which maps E to E into y. So, image of P will go to f of P in y. The function f is said to be continuous at the point P if we draw a neighborhood for a given epsilon r greater than 0, or if we draw a neighborhood of the point epsilon r neighborhood of the point f p in the metric space by D, then corresponding to this neighborhood there exists a delta neighborhood of P in X such that image of any point X inside this delta neighborhood will fall within the epsilon neighborhood of f p. Then we say f is continuous at P. So, it is just like a similar definition which we have used in epsilon delta definition over the real line, over the point in a on the real line in an interval a p. Okay. So, that is a general form, and if P is suppose an isolated point, then the function will remain continuous. So, this is very just a remark, we can say that if P is an isolated point, if P is an isolated point of E, if P is an isolated point of P, then for any epsilon greater than 0, then for any epsilon greater than 0, for any epsilon greater than 0, we can pick up a delta depends on say epsilon and the point p, of course, greater than 0, so that the point x, so that the only point p x belongs to E is basically for which this result holds d by dx x p is less than delta is nothing but x equal to p, because p is an isolated point. So, basically in the neighborhood of the point p within arbitrary small delta, there we cannot get any other point except p. So, for this point we can assume any epsilon the image will fall within always this region. Then clearly obviously the image of this f of x f of p under y will remain less than epsilon, because there is no such point, only the point x will be p itself, So, the image will be 0. So, for any arbitrary epsilon greater than 0, this condition always holds, because if p is a isolated point, then there is no such x different from p available, only the x will be p itself, and as soon as you take x is equal to p, the distance between f p to f p becomes 0, and this will always be less than any positive quantity. Therefore, the function is automatically continuous. This implies f is continuous always at an isolated point. Which is 2. Okay. Now, in this lecture we wanted to give the some relation between the continuity and compactness, continuity and connectivity. So, those results are interesting, that is, we have seen that image of a open set or image of a closed set under a continuous function need not be a closed, or open set need not be an open set. So, this will give a very big gap, that we cannot assure that image of a open set under a continuous function will always remain open, or image of the closed set will always remain closed. That is not that we have seen a counter example for it. However, in case of the compact set, this is very interesting result. If x is compact, the f of x will be compact, that we will show. So, the relation between the continuity and compactness, if f is continuous, it is a very interesting one. But prior to this, we need a definition of the continuity in terms of the inverse image of the open sets. So, that gives a result which can also be treated as a definition for a continuity. A mapping f of a metric space x d say here dx of course we write into a metric by d, a mapping f of a metric space x d into a metric by d is continuous on x, if f inverse v is open in x for every x d in x for every open set v in y. That is, the meaning is that f is continuous on x if and only if inverse image of the open set is open. Inverse image of an open set is always open. So, that gives another criteria to judge whether the function is a continuous or not. So, that is in testing, particularly it is used when the topology in topology normally the definition of the continuity is taken is this way. The inverse image of the open set is open, then the function will be said to be a continuous. Let us see the proof of this thorough, because it will need like that. So, what is a, suppose f is continuous, suppose f is continuous, f is continuous on x, f is continuous on x. Okay. We wanted the inverse image of the open set is open. So, let us take V be an open set, V is an open set in Y. In order to show the inverse image of V is open, what is required? It is required to prove that every point of this set F inverse V is an interior point. So, if it is interior point, then F inverse V will be open. Okay. So, this we wanted. So, let us pick up a point here. So, suppose P is a point belonging to X such that F of P is in V. So, what do you mean? It means that is F P is taken in the set of F inverse B. Okay. That is what it means. Now, we wanted to show there exists a neighborhood around the P which is totally contained in F inverse B. Okay. So, let us start with this. What is B? Since B is giving to B, since V is open, it is already given, and F P is a point in B. This is the point in B. So, we can find a epsilon neighborhood around the P F P which is totally contained in B. So, there exists an epsilon greater than 0 such that Y belongs to capital Y if the distance of F P from Y under the metric Y is less than epsilon, is it not? Distance of this is less than. So, this Y belongs to Y. Since B obvious, there will exist this Y, and since F is continuous, at P. So, for a given epsilon greater than 0, there exists a delta neighborhood in the domain where all the point in the delta neighborhood the image will fall here. So, because it is continuous, so there exists delta greater than 0 such that the image of this d of by f x f p this less than epsilon provided the distance between x and p under y is less than delta. This by definition. Okay. But all the point which lies here, the point y belongs to capital Y. If this is all the point with this x 1 less than delta, this condition holds. So, this condition means f x is in the epsilon neighborhood of f p. So, x must be the point of the inverse, but no sorry, but if x belongs to f inverse p, f inverse b, that is f x belongs to b, then that is f x belongs to v, then what happens there? If f x is in v, f p is also in v and it lies in the epsilon neighborhood of b and f is continuous, therefore, this continuity for this epsilon this holds, it means the continuity of f follows. So, because of the continuity we get that so that distance between f x f p will remain less than epsilon. Now, I will just explain what we did. In fact, what we have taken is that this is okay. First, we have taken a V as a open set in Y. Okay. Then we have fixed up the since P is already taken, the image will be f of P belongs to f B. So, f B is here. Now, since this is on f is continuous at P. So, what we get, there exists a delta greater than 0 such that whenever the point x lies between the delta neighborhood, the corresponding image f x and f y less than epsilon. So, what this shows? This shows the point x, if it is in f inverse B, the f x must be in B. So, once it f x in B, then the distance of this because less than epsilon. This shows there exists a neighborhood around the point f B, which is totally contained inside B. So, V is an open. So, this contain, therefore, this will be an open set. So, f inverse B is interior point, P is an okay. So, P will be an interior point totally, because this is our f inverse V. Okay. So, this will be interior point. Now, conversely, suppose f inverse V is open in X, for every open set, V in Y. Then we wanted to show f is continuous. So, let f belongs to P belongs to X and let epsilon greater than 0, continuity at the point. Okay. Let us consider the set B as the set of those points y belongs to capital Y such that the distance of this point y with f p in the metric dy is less than epsilon. Consider this set. So, this is basically an open ball centered at f b with a radius epsilon. So, obviously, this will be an open set. So, this is an open set. Okay. So, there is nothing prove it. So, once it is open set, according to our assumption, the inverse is also open for every. So, this implies that f inverse V, this will be an open set, is open in X. Okay. Hence, once it is open, so there exists a delta. So, every point is an interior point. Hence, there exists delta greater than 0 such that X belongs to f inverse B as soon as the distance from P of X under the metric is less than delta. It means, because it is open, so we can find a neighborhood around the P which is totally contained inside this neighborhood. So, this X will be the point inside that neighborhood. So, it belongs to A as soon as this comes. Okay. But if X is an element of f inverse V, then the image f x will be in B by definition f inverse. So, when f x in B, so what we get? So, the distance of f x from f b under the metric y will remain less than epsilon, because of this, because as soon this point is in B and for all y which are in V contains those y whose distance is less than epsilon. So, this point f x minus f x comma f b under the metric y is less than epsilon. So, this shows. Now, this shows the f is continuous. at P, and that proves the result. Okay. So, this particular result will be used for establishing the relation between the compactness and continuity. So, let us see, the result is relation between continuity and compactness, between continuity and compactness. Theorem. Suppose f is continuous. F is continuous, mapping, if it is continuous mapping of a compact metric space, of a compact metric space X. X is given to be compact, this is important. X is given to be a compact metric space. Okay. X into a metric, into a metric Y, metric space Y. Then the result says f of x is compact. So, a very interesting result, the image of a compact set under a continuous function will always be compact. And in fact, as a particular case we have seen that if you take any closed interval, the image of closed and bounded interval in R 1, because closed and bounded interval in R 1 is a compact set. So, image of the closed and bounded interval under F is coming to be compact, and even the a cell K cell in R n space or in R k space is a compact set. K cell in R k space is a compact set, because R k space the K cell is a compact set. So, closed and bounded interval will be compact, but if you take only the closed set, okay, and not bounded, it may not be a image, may not be a closed set. Okay. It may be different, that we have various counter examples we have seen where this, but this. Okay. So, in order to show it is a compact set, what we want to prove is that every open cover of this has a finite subcover, and it is already given X is compact. So, with the help of this we will establish this result. So, let us suppose V alpha be an open cover of X, open cover of X. Okay. Now, once it is open cover, it means each element, each point V alpha, when alpha is index set, is an open set, and since F is continuous. So, by the previous result, the inverse image of the open set must be open. So, F inverse of V alpha for each alpha is an open set, as F is continuous function. Okay. So, this is open, that one shows open. Okay. Now, what is given is, given that X is compact. So, any open cover of X will have a finite subcover. F inverse V alpha is an open set in X. So, the and F V alpha is an open cover. So, correspondingly we can say this will behave, the alpha belongs to India is, if we choose this as an open cover for X, then since X is compact, there must be a finite subcover for it. So, compact, and the sequence of this is an open cover of X. So, there exists the finite subcover, there exist indices say alpha 1, alpha 2, say alpha n, such that the finite union of this F inverse V alpha 1 union F inverse V alpha 2 union F inverse V alpha n will cover X, because X is compact. Okay. Now, since our set E, since for every E which is a subset of Y, for every E which is a subset of Y, we have this f of f inverse E. F of f inverse E is contained in E. This is true. Okay. If E is a subset of X, this may not be true, it is a opposite direction, but this is true when E is a subset of Y. Okay. Then using this use on 1. So, apply on 1, what we get? F of x is contained in V alpha 1 union V alpha 2 union V alpha n. So, f x is covered by a finite union of the open interval open sets. So, from this open cover we can identify a finite subcover which covers the f x. Therefore, f x is compact. Okay. So, that is very interesting, clear. Now, we next result we will show it the relation between the continuity and the connectedness. So, the relation is relation between continuity and connectedness. This is also we prove and write in the form of theorem. The theorem is if f is a continuous mapping f is a continuous mapping of a metric space capital X of a metric capital X into a metric space Y into a metric space Y, and if E is a connected set E is a connected subset of E, and E is a connected subset of X, subset of X, E is a connected subset of X, then f of E is connected. If f is a continuous mapping of a metric space X into a metric space Y, and if E is a connected subset of X, then image of this connected subset will also be connected. Okay, let us see the proof. Okay. So, assume that contrary, suppose f e is not connected, then we will reach a contradiction. So, if it is not connected means that is f e can be expressed as the union of the two sets A and B, where A and B are non-empty separated subsets of Y, that is A bar intersection B is empty, A intersection B bar is empty, that is by definition. Okay. So, that is of this part. So, when A bar intersection of this and this is non. Okay. Now, let us take then G, we can write it, put G as E intersection F inverse A and H as E intersection F inverse B. Okay. Now, if we take this, what is our F E? This is set E, this is set E, here this is F E, this is F E. we have assumed Fe is not connected. It means there are the two sets, say A and B, okay, such that this condition is satisfied. Now, find out the inverse of this. So, we are getting F inverse A here, F inverse B here. Now, if I find the intersection with A, E intersection F inverse G, A and E intersection F inverse G, then obviously G and H will be non-empty set, because Fe we have already assumed is a not connected set. So, there are the non-empty sets A and B are non-empty, whose union is Fe and they are separated. So, inverse is intersection of this will be non-empty. So, clearly G and H, clearly G and H are non-empty, first thing. Okay. So, there is no problem in it, and also the union of G H is nothing but E, union of this is nothing but E. Okay. They are non-empty, means neither G is empty nor H is empty. Okay. Now, since our A is always contained in its closure, it is always contained in its closure, and F inverse image of this A closure, which is a closed set, A ball which is a closed set. So, inverse image of the open set is open, it can be extended to the closed set. Inverse image of the closed set is closed if F is continuous. So, F inverse A G will be a inverse image will be a closed set. Okay. So, that is not. So, if it is closed and G is there, so we can say G is contained in, because G is already contained, G is a subset of this F inverse A. From here G is a subset of F inverse A. So, if we replace this A by a bigger closure of it, obviously G will remain as a subset of this. So, we can say G is further G is contained in F inverse A closure. Okay. That is, since this is closed set, is closed. So, obviously, all the limit point of this must be here. So, the limit point if I take, then of G, closure of G, if I take all the point set point of G including the limit point, then obviously it will also be contained inside it. So, this is correct. So, once it follow, then what does it mean? It means F of G closure is contained in A closure. This is one thing. So, let it be 1. Okay? F of G. Now, what is our H? The H is this, E intersection F inverse B. Okay. So, F of H, since H is F intersection F inverse B. So, F of H, sorry, in the E, this is E intersection. So, F of H will be what, and what is our E? Where E is the E is, we have taken this one, no? Is connected F E is, and F E is, sorry, F of E is this A union B, and A union B they are separated set, satisfy this condition. So, if you find the F of H, then it becomes F E intersection B. So, that is equal to F E intersection B, and then when you find the intersection with this, obviously it comes out to be B. So, F of H will be B. Now, F of G inverse, G closure is contained in A bar. A bar intersection B is empty. A bar intersection B is empty, and A bar intersection B is empty, because A and B are separated set, These are separated set. So, this is empty set. Therefore, when you find the intersection of G bar with our H, what happened? Intersection of G bar with H, that is nothing but an empty set. So, intersection of G bar and H. So, intersection of G bar intersection H is empty. Why? Because G bar is contained in this F inverse A, okay. H is B, F inverse A is contained in A bar, and this G bar is contained in F inverse A, and this H is E intersection of this. So, when you find the G bar intersection H, they will be disjoint, and empty. So, we conclude this. Similarly, we can say G intersection H bar is empty. So, this shows G and H are they are okay. So, G and H are separated set, are separated sets. So, but E is the union of G and H, is it not? So, but E is the union of G and H. So, a contradiction. So, it is not possible. Therefore, this this contradicts that E is given to be connected set, E is connected, and its contradiction is because of a rogue assumption that we have assumed that F E is not connected. So, this implies F of E is connected. Okay. Is okay or not? Because why it is 5? Because G bar is contained in this, okay, and H is B, where these two are disjoint, these two are. So, therefore, the intersection will be empty set. Okay. So, that is what. So, this shows our relation between the this one. Now, a similar relation we can also establish for monotonic functions. So, the relations between some monotonic conditions. So, let us see the monotonic functions. If f is continuous, then what? So, the first result we see, that result which is I will not derive the result, let us just see, let f be monotonically increasing function, f be monotonically increasing on the interval say a b, then the right hand limit of this f x when x tends to plus side, x tends to plus, that is f x plus, that is this is the same as x plus h, h tends to 0. So, f x plus and f x minus left hand limit of this, that is equal to limit f of x minus h when h tends to 0, and then this exists if f is a monotonic increasing function, left hand limit and right limit will always exist at every point, of x of the interval a b. And in fact, we have this inequality, that supremum of f of t when t lies between a and x, will be equal to the left hand limit, which is less than equal to f x, which is less than equal to the upper limit, and which is equal to infimum of f t when t lies between x and b. So, over the interval this scenario is there, means the value of the function f x always lies between the lower limit and the left hand limit and right hand limit. Now, if both are equal, then we say the continuity follows. If they are not equal, the point will be the point of discontinuity. The question is, how many such points is possible over in the interval a b if the function is monotonically increasing function or monotonically decreasing function? Will that set of points where the monotonically increasing function exists there in that, will it be countable or uncountable? The answer is that set of all points where the monotonically increasing or decreasing function is not continuous forms a countable set. So, that is the main result which I wanted to show. Okay. So, let us see what is that monotonically, because this will help in getting the result. So, I hope that this result we can prove it, or let me see just proof of this result very fastly, and then we can go for it. Okay. Suppose what is given is, this is given that f is a monotonically increasing function. What do you mean f is monotonically increasing? It means what? That is, if x and y are the 2 points, and if x is less than y, then the corresponding image that is increasing on the interval a b means that if a is less than x, less than y, less than b, implies that f of x is less than or equal to f y. If we say it is strictly increasing, then the sign strictly will follow, otherwise. Similarly, for a decreasing, the order reverses. Okay. So, now if we take this f to be monotonically increasing function, then this interval a b is this. Now, here is the point x. So, first I am taking this point t which lies between a and x, and then here I am taking the point when it lies here. So, over this interval the function is an increasing function. So, what will be the upper bound? Upper bound will be x. So, in fact, the least upper bound will be there. So, the set of according to the hypothesis, or this hypothesis, the set of numbers f of t for t lying between where a is less than t less than x, this number is bounded above y f x, because it is a monotonically increasing sequence, and therefore it has a least upper bound. Therefore, it has least upper bound, say a is the least upper bound. Okay. So, clearly hence a will be less than equal to f x. This is true. Okay. Now, we have to show that same. Okay. Now, let epsilon greater than 0 is given. So, if I choose a number slightly lower than a, say a minus epsilon, then there exists a delta. So, that a minus x is, so that a will not behave as an a minus epsilon will not behave as an upper bound. So, by definition of the upper bound, by definition of least upper bound, there exists a delta greater than 0, such that for all x lying between a less than x minus delta less than x and this condition, and this a minus epsilon will remain less than f of x minus delta, which is less than a, because a is the least upper bound. So, if I take a number slightly lower than this, then there is a point lying x minus delta, a point will be available such that the functional value will lie between them. Okay. Now, further, since f is monotonically increasing function, let it be equation 1. Okay. Let it be equation 1. Since f is monotonic increasing function, So, we have that f of x minus delta is less than equal to f of t is less than equal to a whenever x minus delta is less than t less than x. This is by definition of monotonic. Let it be equation 2. Okay. So, if we combine 1 and 2, what happens? A minus x is less than this, which is less than f t, which is less than equal to a. So, combine 1 and 2, can you not say like this? So, combining 1 and 2, we get combining 1 and 2, what we get is that mod of we get modulus of f x t minus a remains less than say epsilon whenever this less than f whenever x minus delta is less than t less than x. Okay. So, from the x, x is point here and here this is the neighborhood left hand neighborhood of x. So, we are approaching from this side, the t is somewhere here. So, what you are doing is the image of f t under a with a is less than epsilon. It means the left hand limit of the function when x approaches plus to x from the left hand side is a. So, this shows this implies the left hand limit of the function is a, that is one thing. Similarly, we can prove the other side. So, similarly we can show if a is less than x, less than y, less than v, then we can see the right hand limit of this is the infimum of f t, where t lying between x and b, and this is the infimum of f of t when t lies between x and y. Okay. So, using this and others we get the results. Okay. So, the last we can obtain by combining these two over the set A, and then if we take over the set say A y, then we get this one f of y minus is the supremum of f t lying between a and y, which is equal to supremum of f t when t lies between x and y. So, this follows comparing we get the results for it. So, but this result is interesting because the corollary of this, the corollary says monotonic functions have no discontinuity have no discontinuities of this second kind, where the limit does not exist, but limit will always exist, lower limit, right hand limit or left hand limit will always exist, they may not be equal. So, the point of discontinuity may be there, but it is not of the second kind. This is clear from here. Now, if the limit does not exist, then there will be a point of discontinuity, and how many points such are there? This can be shown by this following theorem. The theorem says, let f be a monotone, f be monotonic on the interval a b, monotonic on the interval, then the set of points of a b, at which f is discontinuous is at most countable. Let us see the proof of it. suppose for the sake of doing, suppose f is case 1, when f is a increasing function, monotonically increasing function, increasing monotonically. Okay. F is a monotonic increasing function, and let E be the set of all points, be the set of points at which f is discontinuous. Now, this point discontinuity cannot be of second type, only first kind discontinuity there or removable discontinuities. Okay. So, with every point x of a, now with every point x of E, where the point discontinuous point, we associate a rational number, say R x, such that the lower limit, left hand limit of the function at the point x is strictly less than R x, is strictly less than f. Means it is of the first kind, where the limit exists, but both are not equal. So, we can identify a rational number in between. So, corresponding to each point, we can identify a rational number which is 2. Okay. Now, this is a, there is only one point. Okay. So, let us say, since x is less than, let x 1 and x 2 are the 2 point. Okay. Now, when x 1 x 2 are the 2 point, then if the image of this, the right hand limit of the x 1 will, if x 1 is less than x 2, then the right hand limit of this will be either less than or equal to the left hand limit of this, because x 1 lies here, x 2 is here. So, value at the point x 2 will always be greater than equal to value of this. So, left hand limit of x 2 will at the most coincide with the right hand limit. Okay. But if x 1 is different from x 2 and x 1 and x 2 both are the point of discontinuity. So, we can identify the rational number R x 1 and R x 2 which are different, but we see here, we see that from first that the rational number R x 1 is not equal to rational number R x 2, because these x 1 and x 2, these are the point of E. So, what we have, this implies if x 1 is, this implies x 1 is different from x 2. Okay. So, if x 1 is strictly less than x 2, okay, and if this is R x 1 will be different from, if x 1 is different from x 2, then x 1 is also point of discontinuity. So, we can get the R x 1 corresponding to x 2, we get a point x 2, when x 1 and x 2 are different point, then in that case we do not have this. It means that corresponding to each point x 1 there is a rational number, and vice versa. If the rational numbers are there which satisfy this condition R x 1 is not a, then the point x 1 x 2 we can identify which are the point at which the lower limit and the upper limit do not coincide. That is, it is a point of discontinuity. So, there is a 1-to-1 correspondence. So, there exists 1-to-1 correspondence, between the set E, and a subset of the set of rational numbers. But the set of rational number is a countable set, and there is a 1-to-1 correspondence between this. This implies the set E is countable. So, what this shows, E is the set of those continuous. So, this means that f continuous interval, that is the set E of all points where f is discontinuous on is a countable set, and that is we wanted to show. Okay. So, this proves the case. Thank you very much. Thanks.